Hi, Kim Gang. Boy, do we have a super important video today about the relationship between electron configurations and the periodic table. So my goal today is to teach you some of the different ways of writing electron configurations, but using the periodic table as essentially your cheat sheet on how to do that. So we're starting here with the electron configurations and the periodic table assignment, and I'll go over the answers very quickly. Um, this first model here by team one, there were probably two patterns I wanted you to see. First of all, these underlined portions, the ending portions, all end in S1. Okay, we sometimes call those the electron addresses, and we're going to talk a lot more about that throughout the video. Uh, Also, very importantly, is when you look at the sequence of orbitals filling, whether it's a short sequence like this or a long sequence like this, okay, they're all the same. This one starts off 1s2, 2s1. Okay, this one starts off 1s2, 2s, and then goes to 2p and 3s. If we look at the longest one, it still starts with 1s, 2s, 2p, 3s, and then it keeps going 3p, 4s, 3d, etc. This sequence of number letter combinations, which represent subshells, is the exact same sequence we see in diagrams like this one. 1s, 2s, 2p, 3s, 3p, 4s, 3d. Right? So that sequence, in this case of increasing energy, is the same for every single element when we write the electron configuration. And of course, we're not worried about the superscripts that follow it here. That tells you how many electrons are actually filling these sets of orbitals that we see here. So that's one of the basic principles of um, electron configurations. You probably saw that on the boarding house model, understanding that the lowest energy orbitals fill first. In the boarding house model, it was the lowest floors of the boarding house. Now, for using the periodic table to essentially be your cheat sheet in writing these, it's going to be a way of knowing what that sequence was without having to read it off a diagram like we just looked at. There are lots of patterns on the periodic table when we fill the periodic table with a bunch of electron addresses. Right? So the first kind of bullet point here is about the blocks of the periodic table. Okay. Um, the addresses that all have an S in them are all over here. That's called the S block. There kind of is one exception because helium should really be in the S block. This element here is helium. It's a special element for reasons we'll learn about later. You can consider it sort of belonging here when you're talking about electron configurations, and we'll talk in the next part of the unit why it's actually placed over here. But if you moved helium from here to here, then you have a perfect S block. It would also make the P block look a little bit better because there wouldn't be this thing sticking off that's not really part of the P block. Right? But then there would be a block on the periodic table that all has P's in their electron addresses. And then the D block would be right here. They all have D's in their electron addresses. And at the bottom is the F block. So it is very important that you sort of memorize these blocks. Again, if you were taking a standard test where it's not open book, you would have to look at a regular periodic table and know which block is which. And I'm going to give you a handy way of remembering this. There's a couple reasons why you need to remember this sequence SPDF. One is this pattern that we're going to talk about in just a second, but the one we're talking about right now is the thickness of the blocks. Okay, S is the thinnest block. It's 2 elements wide. P is the next thickest block. It's 6 elements wide. D is 10 elements wide. And F is 14 elements wide. So if you remember the sequence SPDF, then you'll remember the blocks from the thinnest to the widest. And I know you're not going to forget this because smart people don't forget gimmicks. Okay, did you get that? Smart people don't forget. All right, I hope you're with me on that one. All right, let's look at some more patterns going on here. The principal energy level pattern is really important, okay? So remember, the principal energy level is the first number in these electron addresses, and when you look at a set of orbitals, and it's always increasing as you go down. So in the S block, it goes from 1 to 2 to 3 to 4 to 5 to 6 to 7. In the P block, it goes from 2 to 3 to 4 to 5 to 6. In the D block, it goes from 3 to 4 to 5 to 6. Of course, we don't see those examples yet, but we suspect it follows the pattern. And in the F block, it goes from 4 to 5. Okay. So there's another pattern here that I alluded to before, is that each block starts with a different principal energy level. Okay, the S block starts at the top with principal energy level 1. The top of the P block is right here with principal energy 2. Top of the D block is right here with principal energy 3. And the top of the F block is right here with principal energy 4. All right. Um, Given that, you can fill in the subshells everywhere on the periodic table just by knowing your blocks and knowing this pattern that they start at energy level 1, 2, 3, and 4, respectively. All right. And finally, the last piece of the pattern is the superscript number, which indicates the number of electrons filling the orbitals increases by 1 each time you move across the periodic table. So in the S block, it goes from 1 to 2. And of course, the S block is only 2 elements wide, so it stops there. The P block would start with 1, 2, 3, 4, 5, 6. Okay, and again, some of those numbers are missing here, but the missing superscripts would be 1, 2, and 4. Right? And the D block would start with 1 and go all the way through 10. And the F block would start with 1 and go all the way through 14. And again, those superscript numbers tell you how many electrons are filling the subshells. All right, and we're going to go back to that for doing patterns off the periodic table in just a second. Let me just answer question 3 really quickly. This is a pretty easy one. I'll show you the diagram in just a second. But it's how might the orbital energy levels diagram show a difference between the Bohr and the Schrodinger model? So let me just transfer over there. All right, so here we are. Here's the diagram we're looking at. And the difference is the primary energy level or principal energy level is kind of like the Bohr model. In the Bohr model, there's just an energy level based on the orbit. But in the Schrodinger model, there's this splitting of the orbitals into sublevels. So this kind of shows the splitting, and there are the sublevels. Here's the splitting of level 3 into 3 sublevels, splitting of level 4 into 4 sublevels. So Schrodinger's advanced model includes the sublevels. Bohr's model would just have one energy level without being split up at all. Okay, so back to the pattern on the periodic table. So the important thing about this is the electron address tells you which subshell the last electrons are being placed in the electron configuration. So if we were to point to this element here, and we'll figure out what that element is in just a second, it ends in 6p3. What that means is the last 3 electrons to go into the electron configuration would go into the 6p subshell. So let's go back and take a look at one of those other diagrams again. All right, so here's your orbital energy level diagram, and here's 6p. I just fit that on the screen here, but we would have to put 3 electrons into here. The important thing, though, is that all the other subshells below it have to be filled with electrons. Again, we saw that in the boarding house model POGL. Right? So what that means is to get to the 6p subshell, first we have to fill up the 1s, and then the 2s, and then the 2p, etc., all the way up to the 6p. So we're going to have an electron configuration that shows all of these subshells filled, and then the last subshell is the only one that might not be filled. So what does that look like? So first I'm going to show you how to do it on this diagram, which is actually marked off by the subshells, and then I'm going to actually do it using a regular periodic table. And I'm going to be using what's called the superscript notation, which includes the subshell designation plus the number of electrons that are filling that subshell. All right. And if we're trying to get to 6p3, right, it means that we have to fill all the subshells before it in order. And the way to do that is simply move across the periodic table from left to right and top to bottom, which you will notice is the numerical order for the atomic numbers, and just think about which subshell we're filling each time. And we've already sort of blocked out the periodic table and learned the pattern in the principal quantum numbers so that we know what the subshells are. Okay? In other words, to get down here on the periodic table, we start in the upper left. And we first fill the 1s subshell, which is really this element and this element. Okay? And then we just keep moving left to right and top to bottom. We then fill the 2s subshell. and then the 2p subshell, and then the 3s, and then the 3p, and then the 4s, and then the 3d, and then the 4p, and then the 5s, and then the 4d, and then the 5p, and then the 6s, and then be careful here. This asterisk shows us that this little section should be squeezed into the periodic table here, okay? And that is the 4f section. Okay? And then these would be the 5ds. They're not marked in this version, but again, there's a pattern. Okay? And then finally the 6p's. So that's the order in which we're going to fill the orbitals. And again, that's the exact same order we see on this diagram down here. Okay? So let's do that using a regular periodic table, and we'll actually write it out. Okay, so here's a real example with a real element here. So we've got the periodic table, and the element I was pointing to there was bismuth. Okay, it's the 83rd element, which means I need to place 83 electrons in the configuration. But like I said before, I'm going to start in the upper left, and I'm going to imagine which subshell this is. So this is the S block, and it's the first one. So down here, I'm going to write 1s for the subshell. And if I'm going to fill that, that means I have to put 2 electrons in it. Right? So that's the first part. Okay, and remember, helium over here is really part of the S block, so those are the first 2 elements. Then for atomic number 3, I'm in the 2s subshell. So I write 2s for the 2s subshell, and I have to fill that, so I put 2 electrons in it. And that means I've put 4 electrons in, which would be enough to show the element beryllium. But I need to get to 83 electrons, so I keep going. Right? So the next set of electrons are in the p block. And remember, the p block starts with energy level 2, so I'm going to write the 2 p's in here. And it gets filled with electrons. Remember, this block is 6 elements wide, so it's going to get filled with 6 electrons. Okay. Here's a quick reminder why the p block is 6 elements wide. It's because the p orbitals always come in sets of 3 in their subshell. And if you can fit 2 electrons in each one, that's going to be 6 electrons that can fit there. Okay. Likewise, the d block always involves 5 orbitals, and that's why it's 10 elements wide. It can fit 10 electrons. And the f block has 7 orbitals in each subshell, and that's why it's 14 wide. So now we're continuing on the electron configuration to get to bismuth, and so far we filled 10 electrons, which filled up the 2p subshell. So we're back over here to the s block, and you'll notice we already have the 2 s's, so this must be the 3 s's. And it must be filled, so I'll put 2 electrons in it, and now we have 12 electrons. Okay? Continuing along the periodic table, we're back in the p block, and we already had the 2 p's, so this must be the 3 p's, and it must be filled, so there must be 6 electrons in it. And that gets us 18 electrons now. So that would be enough to show the configuration for argon. We still got a ways to go, though. So I'm back over here in the S block. Okay, we already had the 3 S's, so this must be the 4 S's. And it must be filled, so there's 2 electrons. Okay, and now, for the first time, we're in the D block. All right, in level 2, you're not going to have to write configurations for the D block, but you should understand what the D block is and its importance. And we can just follow the pattern we've been doing. Okay. Remember that the D block, remember SPD, 1, 2, 3, starts with a 3rd energy level. So these are the 3 Ds. Okay. And it must be filled. We just went over the idea that there are 5 orbitals, so it can fit 10 electrons. All right. So we're now up to 30. We're going a little bit quicker here, but we're still not there. So we're back in the P block. We previously had the 3 Ps, so this must be the 4 Ps. And it must be filled with electrons, so there must be 6 electrons there. And now we're up to 36. Okay. So we just keep going. Numerically, we go back to 37, and we're back in the S block. This now must be the 5 S's, because we already had the 4 S's, and it's filled with 2 electrons. Okay. Now we're back in the D block. Okay, and we already had the 3 Ds, so this must be the 4 Ds. And again, that must be filled, and that takes, 10 electrons. So now I'm all the way up to 48 electrons. Okay, that's enough to fill the electron shells for cadmium. All right, and I'm going to go right ahead and do the remaining ones, and then skip to the end because we're almost out of time.